Okay, so we're just going to go through some fundamentals of the FinFET devices, and the first part of the talk will just go over planar MOS devices and sort of review the background of MOS operation as a switch, and that'll motivate what led to the development of FinFET technologies. We'll see like what the shortcomings are with a MOS device, and then once we get into FinFET device, then we'll see how it helps overcome some of those shortcomings of the MOS operation as a switch and improve logic speed and power trade-offs as a result. So it'll be clear there that the motivation behind FinFETs and the benefits that are derived from them are mostly focused on digital logic. And so, for analog design, there can be some challenges in particular that arise. So we'll spend a few slides talking about that and just finish out with a couple slides showing an example of FinFET design that was done in our lab. So basically, when you think about use of MOSFETs in digital logic or in VLSI, they're basically being used as a switch in some kind of logic gates in this configuration, right? There's pull-up logic that's switching and directing current from VDD onto the output on rising transitions, and on falling transitions there's some other switches in a pull-down network that are drawing current away from the output and making the falling transition. So the key performance parameters of the constituent switches here are that, for high-speed transitions, you want them to conduct a lot of current when they turn on. So I'm going to call that I on, right? That's the amount of current that the switch conducts when they're turned on. So generally we want our logic to have higher speed, and at the same time it would be great if it also has lower power. So the power consumption of logic gates, you can think of them as being primarily determined by two components. One is the energy consumed per transition. That's our dynamic power consumption, and that depends primarily on C, the capacitance in the logic, and VDD squared, right? So that's the energy per computation is C VDD squared. That's how much energy gets dumped onto the cap and then pulled off of it, so wasted in each transition. And then the power is just how many times that happens per second. That amount of energy is dissipated per second. So if we want to have low power logic, there's two terms here, obviously. We want low capacitance C. The capacitance in turn has two components. There's the parasitic capacitances, and then there's C aux, which is the gate oxide capacitances of the transistors themselves. In some sense, C aux is kind of a friendly capacitance, right? Like we need it in order to turn the gates on strongly. The C parasitics, as the name suggests, they're just extra capacitance that we wish to minimize. Second important term here, even more important, is VDD. It appears squared, right? So a really good way to lower power is to lower VDD, lower the dynamic power. And the other component to power consumption is the leakage current, right? So that's determined by the current that flows through those switches in the pull-up and pull-down logic when they're off. So we call that I off. So bottom line is that, what do we want from our technology in order to advance VLSI? We want small transistors as possible. That just lets us have a lot of dense functionality all on one chip. And so there's benefits in integration just from having small transistors. But we would also hopefully like those smaller transistors to let us have smaller capacitances, which will then hopefully turn into lower power as well. What we really want to do is, in order to combine high speed and low power consumption, we want to combine in the switches the ability to have high on current, low off current, so low leakage, and low VDD to lower the power. But we're going to see how all these are related in a way that makes it fundamentally challenging to combine all those at the same time. So we'll start considering each one in turn. First, I on, right? What determines the on current? Let's think about what happens in this sort of toy logic gate over here as it undergoes a falling transition, right? So the pull, this should be labeled pull down logic, right? The pull down logic is activated, and the output capacitance is discharged by the on currents of these switches. And as it does, right, obviously there must have been a rising edge at the input to turn on those gates. And then a short time later, the output falls. So the on current is sort of the average of the current flowing in the pull down logic throughout this entire period of time. And so you can think about it as going through a couple different sort of states. Initially, the input's rising just above the threshold voltage of the pull down logic. And so that's signified by this green symbol here. That's when the pull down logic is first barely turning on. At that instant, the output is still high, right? So at this period of time, signified by the green symbol, if we think about the IV relationship of the transistors in the pull down network, it's the transistors living somewhere over here. So VGS is just barely above the threshold voltage. So we've got this relatively low ID. It's just starting to conduct, but VDS is still very, very high, right? Then as the transition proceeds, the output voltage drops. So VDS on the pull down logic transistors drops. But, you know, the input's still rising. So at some point, you know, the input reaches all the way up to VDD. So at that point in time, the on current is living up here. It's signified by this red diamond symbol, right? At that point in time, we've got a much higher VGS, but we've got a lower VDS because the output voltage has started to drop. And then eventually, the output voltage drops all the way, and it follows this curve all the way back down to VDS equals 0. But really, the key point in time is as we're going from the green to the red symbol here, right? That's the key part of the logic delay. And during that period of time, the transistors in the pull-down logic network are going somewhere sweeping along this arc here from the green symbol to the red diamond here. So the logic speed really depends on kind of average. The on current, I on, depends on average of all those currents all through that transition. And that'll be important later. We'll see different physical factors come into play. What about the off current, I off? So here, you know, usually we think of a MOSFET as operating following a square law, but once we turn the transistor off, VGS is way below the threshold voltage, would be at 0 volts. So we expect only a very, very small current. This leakage current is non-zero though, because when we're operating in subthreshold, right, so the VGS is below the threshold voltage, we see that the MOSFET follows an exponential voltage-current relationship. So as a result, when it's plotted on a semi-log scale, as it is here, VGS versus drain current, right, you end up, because it's exponential, you end up with a straight line on the semi-log plot. And it intersects here at VGS equals 0 at some finite value, some non-zero value. That is the our I off, right, our leakage current I off. So, you know, we'd like to minimize this value, like we said, to minimize the leakage current component. So what determines it? Well, a couple things. Obviously, the W over L of the transistor has an effect. The bigger the transistor, the more leakage current is. It's fine. Second important thing, if we think about the technology, though, that the W over L is determined by the designer of the circuit. If we're thinking about designing a better transistor, though, the parameters that are more of interest to us might be something like VT. If VT is increased, this whole subthreshold curve shifts to the right, and obviously we're going to end up with a lower I off. So the off leakage current obviously depends on VT in that way. The second important parameter, though, is the slope of this exponential. We're going to call that the subthreshold slope, and that is really a key knob that we have to play with in designing a new technology. So we will see that the subthreshold slope, the slope of that part of the curve, in turn, depends on this transistor parameter that we're going to call N. So N is essentially related to the ratio of Cox, which is our gate oxide capacitance. That's the capacitance through which we actually turn the transistor on and off, through which the field effect happens of the FET. The ratio of that and this kind of backgate capacitance, so the capacitance between the body and the channel, the junction capacitance, CJ0. So that ratio determines N. So N shows up in the subthreshold current I off as shown here. So in subthreshold we have this exponential voltage current relationship, essentially because when the channel is not inverted you end up with an NPN structure, so it behaves kind of like a BJT. So not surprising you get this exponential relationship here. The exponent here depends on the gate overdrive voltage, V effective, which is going to be negative in subthreshold, and it also depends on N, our subthreshold slope. So for planar CMOS devices, this ratio N is somewhere around 1.5. It's kind of hard to make it much smaller than that. So our off-state leakage current, I off, will be found when VGS is 0. When VGS is 0, the effective gate overdrive voltage here is actually negative VT, right? So we plug that in, negative VT here. What we end up with is the off-state current given by this expression here. And so obviously the key term here is the exponential, right? And if we zoom in on the exponent, what we see is that we're going to make this exponential term a lot smaller if we make VT bigger or if we make N smaller. So those are our technology parameters that we're going to play with. Q is fundamental electronic charge, not much we can do about that. K is Boltzmann's constant, T is temperature, nothing we can really do there. So really the main knobs we have are VT and N. So, taking a step back, recall that we want to combine high on current and low off-state current, and at the same time, low VDD for low power. That's going to give us our combination of speed and low power. So we've seen now that I on increases with the gate overdrive that we have when the transistor's on. So that is going to be VDD, that gate overdrive voltage is VDD minus VT. So obviously if we have higher VDD, we're going to have a higher overdrive voltage, we're going to have more on current. Nothing surprising there, right? Higher VDD lets us turn on that transistor harder. But we'll also see that, right, if we have a higher VT, then we're going to have less overdrive voltage, so we're going to have less on current. On the other hand, the off-state leakage decreases exponentially with VT over N, and also depends on temperature. So the problem with VT is that if we increase it, we get better leakage, but worse on current. If we decrease VT, we get more leakage, but more on current. So it's hard. We can't really win too much by playing with VT. It's just a trade-off between on current and off current. And in a sense, we can always trade off on current and off current as designers just by making the transistor bigger and smaller anyway. So that's not really very exciting. So what we really, what designer of technology really thinks about, and if they're trying to make a better switch, is to improve this ratio of I on over I off, right? If you improve that ratio, then you've really done something, right? So you might say, okay, no problem, let's increase VDD. Because if I increase VDD, I've got more gate overdrive when the transistor's on, but it doesn't affect the off current at all. So that's true, but then that is going to make our power consumption blow up. So that's where we end up in this tough trade-off, right? There's nothing obvious we can do there other than N. We haven't talked about N yet. N is really the key parameter, because if we can decrease N, you can get an exponential improvement in the leakage current without affecting the on current and without affecting VDD. So that's why the focus is on N. And if you remember what N is, it's the ratio of those capacitances. So it makes sense then that to fundamentally get a significant improvement in N, you need a different kind of geometry for the cross-section of the transistor, right? And that's how you kind of end up at a FinFET. A FinFET by its very geometry is going to give us a better number N, their subthreshold slope, than a planar transistor will. So here's just a cartoon picture to kind of help illustrate that, right? So this picture is maybe turned sideways compared to the way you often picture it, but here the gate length is in this dimension here for the planar MOSFET. The idea is the drain is back here and the source is at the front here, right? So the current's actually flowing, this way in the picture. So you've got some, N is some parameter that we said is about 1.5 for a planar device. And, with a FinFET, you're basically wrapping the gate around the channel region. So it makes sense. You kind of get more C-aux compared to the parasitic backgate capacitance to the bulk, right? Because you're exposing less of the channel to the bulk region compared to the gate. So you can get an N with this geometry very close to 1. So that's a significant improvement in N, therefore a significant improvement in the subthreshold slope, and you basically have a better switch. So that's a big part of the story of FinFETs. Second big piece of the story with FinFETs that you need to understand is a little bit more subtle effect called drain-induced barrier lowering. So So DIBL, or sometimes it's just called DIBL for short, you know, is a little bit more subtle effect. We won't go into all the physics of it. It's, you know, quite difficult to model. But I think hopefully we can understand it qualitatively just from these cartoons here. So the idea is, here's a planar MOSFET pictured here that's turned on. So there's a positive VGS applied for an NMOS transistor. Channel's inverted, and there's also a large VDS applied. So the large VDS, you've got, you know, a significant, you know, voltage across this junction here between the drain and the body region. And so these electric field lines here are showing up. They're not exactly in parallel with these electric field lines here that induce the field effect, but they're close, right? So the idea is there's a subtle effect there where a large VDS can kind of help the gate turn the channel more on, if you like. Or, you know, the way it's usually modeled is to say that a large VDS effectively reduces the threshold voltage by a little bit. And the effect is really subtle for a long channel device. But when you get a really short channel device, the picture looks more like this one. So here, if you've got a high VDS, maybe it's a little bit more clear. It's not so surprising that a big VDS is somehow, qualitatively, you could say, helping turn the transistor on. And so as we said, we model this with a reduction in VT. It looks like a lower VT. It's like the drain is doing part of the work of the gate, right, to help turn the transistor on. So none of that's very rigorous. It's just qualitative, so you understand qualitatively DIBL, what it's doing. So again here, just by the very geometry of the FinFETs, right, you get this better control of the channel region by the gate. The gate wraps right around it. So the channel's in more complete control of the gate, under the gate, right? And so as a result, again, we're not going to go into the detailed physics of it, but the DIBL effect is greatly reduced in FinFET geometry. And so this is an important second piece of the story here. And you'll see why when we show some more IV curves. So back to, you know, now we're gonna try and see how these two consequences of the FinFET geometry, the lower N and the reduced DIBL, how that can translate into better logic performance for FinFETs, right? So here again, we're back to our cartoon sort of falling edge on a simple CMOS logic gate here. And you remember we defined these two states. When the pull-down network first turns on, we've got this green situation here. So the green situation, remember, is where VDS of the transistors is high. So that's pictured here by this blue curve. So the blue curve is an exponential plot of IDS versus VGS corresponding to a very high value of VDS. So you'll see here you've got in this region subthreshold behavior because we're below the threshold voltage, and that turns into a square law somewhere around here, right? And so the slope is not as steep on the semi-log plot, right? When we're in square law compared to when we're in subthreshold, then it becomes much steeper because we go in subthreshold. The break point here should be the threshold voltage. But because we've got a DIBL effect in planar devices, then the threshold voltage that we see when the transistor first turns on is actually a much lower threshold voltage. It's reduced by the DIBL effect. So VT sat is we're going to use to refer to the threshold voltage when the transistor has a very high VDS. And that's what you see actually when the transistor's off, right? When the transistor's off, you got a huge VDS on it. So the leakage current you see is shifted up a lot because of the DIBL effect. Effectively, you've got a lower threshold voltage when it counts, when VDS is there, right? Then as the transistor turns on, right, VDS is decreased, VGS goes up all the way to VDD, and then you've got a different curve with lower VDS. Now the DIBL's gone, the threshold voltage shifts up to where it should be, VT, and now, sure, you've got low leakage, but you're not leaking anymore. The transistor's on at this point, right? So you've got the curve shown here, right, with a higher VT, which actually means lower on current, unfortunately, right? So the on-state current is, again, kind of the smeared average between the green and the red symbols here. The on current is somewhere around here. The off current is determined by the blue curve, the high VDS. A high VDS curve, right? So So those are the key, right? I on is key to determining the speed of the transistor. I off and VDD determine the power of the logic. So let's see what happens if we introduce sort of FinFET geometry. The first thing we said is that reduces n. A smaller n is going to increase the subthreshold slope. So these curves here, if we reduce n, the subthreshold slope improves, it gets steeper. So if all else stayed the same, it would be very simple, right? We would just have a smaller leakage current and the same on current. So the speed would be kind of the same. You know, here, the way it's pictured here, VDD is the same. So we would just save a little bit of leakage power. So that's kind of nice. But, you know, leakage power is, you know, probably to begin with, not the dominant source of power consumption. Dynamic power consumption is, let's say, in planar technology, still, you know, most of the power for most logic circuits. So what's usually done is this improvement in subthreshold slope is traded off against other technology parameters. So specifically, when you go to FinFETs, n is reduced, you get the steeper slope, but at the same time, you can then afford to reduce VT. So VT shifts over from right to left. VT sat also shifts over. So the off current goes back to where it was before with, you know, the higher value of n. So the leakage is now the same as it was before, but you've lowered VT, so the on current's higher, right? So now you've got, if you make that trade-off, you've got a faster logic gate, same leakage current, and same VDD as before. Furthermore, then the extra trade-off that's made is say, well, what's usually, you can also now take VDD and lower it a bit. If you lower VDD, you give up some of that on current that you had, but now you can greatly reduce the power, the dynamic power, because it depends on VDD squared. So the bottom line is that when you go to FinFETs, typically the trade-off that's made is you get higher subthreshold slope. You can then afford lower VT without making the leakage get too high. And because VT is lower, you can probably also afford to lower VDD and still have a decent speed. And then you save a lot of power, right? So that's the idea anyway. In principle, that's the way FinFET geometry can turn into better logic, a better trade-off or combination of speed and power in logic. By the way, there's analog circuits too where you use switches all over the place. So any circuits like that also benefit. You've got a better switch to begin with. So you know, analog switched circuits can benefit from that too. We haven't talked about DIBL yet. DIBL yet, as I said, is also a big part of the story. If you recognize that FinFETs have lower DIBL, then that is captured by going from this cartoon down to this one. Since DIBL is lower, these two curves get closer together, right? There's not much difference between the threshold voltage and saturation and when it's just in triode. So because of that, you can afford to further reduce VT, right? I mean, without changing the off current, right? We can just leave the blue curve the same and just shift the red curve over to the left a bit by having a lower VT. So now, you know, you got lower VT again. So now I can go and reduce VDD even a little further and save a little bit more power. So these are the two the key benefits, right? The lower N, higher subthreshold slope that results, and the lower drain-induced barrier lowering. And effectively, you can trade those off and end up with lower power consumption. Okay, so that's the main impetus behind this different MOSFET geometry, right? Go to the FinFET. But of course, it's got other sort of ancillary effects too that are particularly important for analog design. So one, right, you may already be in your mind, is that, you know, it all but eliminates the body effect. N is also a key parameter in determining the body effect. And that shouldn't be surprising. I mean, if we've, you know, made it so that the channel is almost completely under the control of the gate, obviously that means the body is not having much effect on the channel. We've practically eliminated the body effect. And indeed, with FinFET devices, you see almost no body effect anymore. So that's kind of interesting for analog design. Also, you know, maybe you're familiar with this plot. This is plotted on the y-axis here as conductance normalized to the drain current, so normalized to the power consumption of the analog circuit, and then the x-axis VGS. So you know you get the best bang for the buck from an analog transistor, the most transconductance per unit drain current when you're in subthreshold, and that limit, it depends on the subthreshold slope, Q over NKT. So if you make N smaller, you can actually get a little bit more transconductance from a MOSFET in subthreshold. So that's interesting too for analog design. As far as DIBL goes, right, reducing DIBL also has some positive impacts on analog design. Basically, with planar technologies, DIBL means that the drain current starts increasing when VDS gets really big, right? Because it kind of lowers the threshold voltage. Effectively, that means at large VDS, the RDS, the small signal output resistance, the transistor comes down. So you get less intrinsic gain with less DIBL effect. So this part of the IV curves for MOSFET, the slope gets shallower, right? And so the RDS of the transistor at that point gets higher. So basically, because of that, you can actually see a higher RDS and a higher intrinsic gain from a MOSFET in a FinFET technology compared to planar technology. So that's kind of cool because intrinsic gain of transistors was getting to be a real problem in 28 nanometer CMOS, and you actually get a bit of an improvement when you go to 16 nanometer FinFET. You get a bit more intrinsic gain. So that's kind of also cool for analog. So all that sounds great, but there's other really important drawbacks and limitations with FinFETs too. So that's what we're going to talk about next. A lot of them come down to the parasitics associated with FinFETs. I mean, effectively, the geometry is so compact now that things are just getting closer together and wires are getting narrower, so you've got more capacitance and more resistance as a consequence of that. Then on top of that, the design rules required to make these really fine geometries is like imposing all these other requirements that makes the parasitics even worse. So basically, the parasitic capacitance can be a really high fraction of the total capacitance in FinFET technology. So that helps take away some of the speed and power benefits that FinFETs provide. Also, the parasitic resistances, right, we haven't talked about them yet, but they also become like a significant fraction of the device performance. So that also impacts device speed and the noise performance as well. And the last tough thing is that because these are parasitics, they're quite layout dependent. So, it's hard to incorporate them early in the design flow, right? Until you work with the technology for a while and you develop a bit of intuition behind them. What you're going to end up seeing is a big change in performance after you do the layout and you do extraction compared to pre-layout. So here's just a cartoon just kind of illustrating some of these things, right? You've got contacts are very very small now, so the contact resistance is large, and of course that contact resistance will appear directly in series with the source, right, with the channel region. So that's going to impact your transistor speed and performance. It also decreases on current, right? So it also impacts logic performance too. The low layers of metal and the poly is so narrow that they also have a significant amount of parasitic resistance. And then finally, you've got these really tight metal pitches, right? So metal's really close together. You've got a whole bunch of parasitic capacitances showing up. So just to give you a feel compared to planar technology, some of these parasitic resistances can go up by 50% or more. The capacitances can go up 20 to 100%. So it's big. It's a big hit from these parasitics. So just to summarize, right, sort of some of the things we talked about so far. FinFETs, the geometry is more compact, so you can get more drain current and more transconductance for a given area, maybe as long as you deal with some of the sort of self-heating electromigration problems that we're going to talk about in a sec. You've also got sort of quantized channel widths, right? But you can't just realize any transistor size you want with FinFETs because you've got an integer number of fins there. That's not such a big deal, in analog design, because usually your transistors are relatively big anyway. So you've got enough granularity, enough resolution in setting the dimensions of the transistor, even with FinFETs. It's not really a problem. But it can be a bit of a problem for some logic and SRAM design where you're trying to minimize sizes so much. You've got that less of a DIBL effect, so that means you got higher RDS, higher intrinsic gain. That's nice. Basically no body effect, so the effect's like less than 10 millivolts. You can basically not worry about it. But you've got all these higher series resistances that need to be taken into account. Although you might have lower junction capacitances for the drain and source junctions, thanks to the geometry, but it's the metal capacitances that are higher, right? So CGD, CGS, CDS, those are all much higher. And then, you know, the particularly problematic thing is that these aspects of performance that make the transistor worse, they're very layout dependent. So you don't know them at the outset, right? And they're dominant. So here's kind of a nice table summarizing sort of the good and the bad. More drive current, you can have more headroom there because, you know, the reduced DIBL effect helps with that. You can have more GM over ID with FinFETs and higher open circuit gain when you make the jump from 28 nanometer to 60 nanometer FinFET. On the other hand, the capacitances can go up significantly. So even though you might have more GM, you have so much more capacitance that the FT seems to hardly improve at all. And Fmax can actually get worse, partly because of the increased series resistances there. So it's not, you know, excellent for very, very high frequency design, right? Like millimeter wave type stuff. There's also been reported increase in thermal noise. Not surprising when you consider you've got more series resistance at the gate and the drain and all that. So here's, you know, now a few slides to you see the, you know, talk about the different layout styles that show up with FinFETs, because that's, again, that's important determining performance because the parasitics are so significant. So this kind of picture is probably familiar to you. It may not be like the best transistor layout you could ever imagine, but you kind of understand what's going on here. Green gate is running vertically here, and you've got a drain and source region in orange and contacts to that, bringing it up to metal 1 in purple here. So with a planar MOS transistor, you had flexibility in the transistor channel width and length, so you could set it to whatever you want, and you had very few, if any, orientation constraints, right? In advanced planar technologies, you have some orientation constraints, meaning that the gates maybe had to run only in one direction, but not too bad. Those get much more significant in FinFET design. So here's a kind of FinFET transistor layout view, a typical one. And you know, you've got the gate running vertically here in green, but the channel width is divided into these individual fins that are pictured here. Each of those lines is one fin. And so, you know, those fins have to appear on a fixed pitch that's defined by the technology. You can't set the spacing of them to whatever you want. They run a constant pitch across the whole chip effectively. So their orientation is always horizontal, the gate's always vertical, and then also the orientation of the low layer metals is also fixed. So typically, you know, you might have the lowest level of metal might have to run horizontally across here, and then you would pick up drain and source contacts as shown here with this orange via 0. You've also got this weird thing, you know, that's sometimes referred to as M0. M0, you can kind of think of it as equivalent to the active contact layer, but you can draw and like you can route short distances with it. So it's not just a point contact. You typically make like a bar with the M0 to contact the source and drain, but it's highly resistive. So you don't want to use it as it's not really a metal layer that you want to be routing over a long distance, right? You would only use it to basically get to a via 0 and then immediately, as quick as you could, go up to metal 1. So that's kind of what's pictured here. So just to give you an example of difference, right? This is a picture taken from my textbook that shows an example transistor layout for a planar technology, and it's actually showing a differential pair. So you've got some of the poly fingers here are being pulled out to the top. Some poly fingers are being pulled out to the bottom. This is showing like a common centroid type layout, right? So Some of them pull out top. The drains and source regions are contacted, and the metal is running right over top of the transistor to route the current out away from the transistor. So that's a typical style for planar technology. In a FinFET, it might look something more like this, right? So you've got the fins running horizontally here. The gates, there's some similarities here. The gates are the green lines running vertically, and their pitch is fixed. You cannot make them closer or further apart. They've got to, if you're going to make a minimum gate length, it's got to stay on that predefined pitch. And the pitch is so tight at this point that you can't exactly contact the M0 layer, with neighboring contacts. That would start violating, probably, depends on the technology of course, but probably start violating some design rules. So you've often got contacts that are kind of staggered in this way, and then you've got some metal, the light pink or purple running over top here, that's picking up the source and drain contacts as they go. So you've got alternating source and drain regions. And again, even those metal layers are probably on a fixed pitch. So you can see the source and drain. You can imagine there's lots of CDS, capacitance between drain and source, because you've got all these wires running right next to each other to pick up the contacts. And then you've got to run the gates out in this layout, this particular layout style. There's other possibilities, but here you've got to run the gates out far enough to be able to contact to them without violating design rules, right? So these vias, there's obviously going to be minimum spacing requirements here to these vias, so the gates maybe have to run out a little bit further, and that adds a bit extra series resistance. So it's just tough, basically, to make all these contacts in such a tiny area and get the current in and out of there without having a bunch of capacitances show up as well, right? So another issue that's was always there in planar technologies, but it's just getting particularly bad in FinFET technology. And this is not really anything necessarily about the FinFET geometry. It's just the shrinking technology, right? Means that the wires are getting thinner, and so electromigration becomes more of a problem. Basically, electromigration arises whenever you've got DC current flowing through a wire. It causes the metal to erode over time and weak spots to show up, and then ultimately it just fails. You just get an open there, it just pops. So mostly all the research, the electromigration is not, I should say, super rigorously understood or modeled. However, all the research suggests that it's mainly arises due to DC currents, but in analog design we have a lot of DC currents running around, so it's a bit of a problem for us. So you can imagine, right, these low layers of metal, they have a really fine pitch, really narrow, so drawing that current out from those many fingers of MOSFETs, all that DC current starts to add up on those really thin wires, and electromigration becomes a problem. So this, as a result, often like the layout of transistors is just limited by this. You can only make transistors a certain size, otherwise you start getting electromigration problems. Another, somewhat related problem is the self-heating effect. Basically, partly because of the geometry, this is partly because of the geometry of FinFETs. The heat dissipation is not so great, right? The current is running through these fins, and so there's not a lot of thermal contact with the bulk region, which would help dissipate the heat and energy, right? So because of that, you can get a lot of heat built up, and also, just the transistors are packed so densely that that you've just got a lot of energy being dissipated in a really tiny area. So as a result, you can get really localized heating events that, first of all, degrades the transistor performance. Higher temperatures always, you get worse, there's a worst case in terms of transistor performance. But at the same time, it can also accelerate electromigration, so that it can cause reliability problems on top of it. So the worst case for electromigration is also high temperature. So, as a result, you see, it's quite common in FinFET layouts that you just see a lot of dummies inserted. I mean, you already see this in advanced planar technologies, but you get a lot of them showing up in 16 nanometers. You got dummies put in everywhere. And sometimes it's just to give some extra space for the heat to dissipate, right? Avoid these self-heating effects. Yeah. So, but, you know, again, because everything's got to be in a regular pitch, you can't just leave more space. You've got to put these dummies in there. That's actually the easiest way to do it. Okay, another interesting thing that you see, or another interesting sort of option that pops up for designers in FinFET is this idea of having longer gate lengths. It is possible to have longer gate lengths with FinFETs. Not everything has to be minimum length, and yet it's quite common that instead of having a long gate, many designers will just choose to stack 3 gates in series, right? So, you know, here, instead of, you know, the example that's given here is you could have one gate with a length that's 3 times the minimum, or you could just have 3 minimum gate lengths stacked in series. So what are the trade-offs there? I mean, at first glance, it would seem that this transistor on the left is preferable because you can have a slight, you know, reduction in area, presumably, because you avoid all these extra source and drain regions in between. And not only that, by eliminating these extra source and drain regions, you can get rid of all the associated parasitic capacitances there. So that should help, you know, reduce total capacitance, reduce power, maybe improve speed. And also for analog design, it should improve the output impedance here because you don't have extra capacitances eroding the high frequency output impedance. But there's a problem. So here's a typical scenario where you might, as an analog designer, you might want a longer gate length. A nice simple situation is where you've just got a diff pair and the tail current transistor M3, or you might say, well, I want that transistor doesn't have to operate at high speed. I want it to have a high output impedance, so I'm going to make it have a longer gate length. The problem is that M1 and M2 maybe are it's a high-speed diff pair, let's say, or you would like it to have a high GM as possible. So those are minimum gate length. And when you're in the minimum gate length world with FinFETs, you've got to be on this very fixed pitch, right? Everything's got to be this set pitch, not just for the gates, but for the low-layer metals. Everything is set. If you're going to switch from that to a longer gate length, there's all kinds of, you know, minimum spaces you have to allow in order to break that fixed pitch and start going to a longer gate length. So if you wanted to realize M3 as a longer gate length, the layout would end up looking something like this. You could have your diff pair up here, then you'd have to have a ton of space and have the tail current down here. Then you'd have to route all the source connections all the way down to here to the tail current, and you'd end up with so much extra capacitance just from the routing that you'd probably lose whatever benefit you were getting in the first place. So instead, usually what people do is they just stick with the minimum gate length transistors and just connect more of them in series, because then at least the layout gets nice and compact. And it gets just really simple, right? Everything, you can imagine here what the layout starts looking like. Everything's on a fixed pitch. And in fact, all you do is you cut these polylines when you want to start a new transistor, right? And you can literally insert these things in the layout called cut lines that just defines a break between one transistor and the next. So, and then that lets everything just go whoosh, you know, just shrink right down. So that's usually the style. So in summary, you can have longer channel devices, but they just, unfortunately, they have to be kind of separated and off on their own. Another interesting trade-off that everybody deals with FinFETs is like how long should each polyfinger be? How many fins should you make it? And so there's a bunch of trade-offs here, right? So just for cartoon, we consider 2 layouts here with fewer fins, 4 fins per finger here. This one has 6 fins per finger on the right. So don't worry about the numbers too much. Those depend on whether you're in 16 nanometer or 7 nanometer or whatever. But the trade-offs are kind of, some of them are evident, right? If you have fewer fins per finger, then the poly gate's not as long. Each finger's not as long, so you can lower the gate resistance. So that can be a nice benefit. On the other hand, if the gates are longer, right, it might give you more room for more contacts for each source and drain region and more metal to pull out all that current. So there's like a trade-off there. So, you know, you might benefit in some cases from having more fins per finger, but maybe you contact the poly at both sides to help with RG, right? These are all different trade-offs that you might make depending on what you're after in your performance. Another issue for analog design in particular is that when you have very few fins per finger, if the transistor W over L is very large, then the transistor starts looking like a really long rectangle, right? So sometimes that can be its own bit of a pain for floor planning your analog layout. So here just showing the trade-off, right, on a sort of large transistor, what the trade-off looks like, and they both these layouts have the same total number of fins, right? But one of them has more fingers, but fewer fins per finger, 4 fins per finger. This one here has more fins per finger and therefore fewer fins. So you see you've got, maybe you've got a nicer aspect ratio here for the layout that might help with floor planning, might help a little bit with matching, although you have to remember the dimensions here are all so small that the matching is usually, pretty good anyway. On the other hand, this style of layout here, right, partly because you've compacted it so much, you're probably going to have more self-heating going on, so you might then have to go back and insert more dummies, right, to let this thing cool off. You've also got, long poly fingers here, so the gate resistance is more. So these are the trade-offs to consider. The bottom line is you typically, 8 fins per finger is a lot. I'll just put it that way, right? Like this, you might tend more towards the top picture, to be honest, in most cases. Here's just from something that was at ISSEC in 2018, just illustrating the trade-offs in the self-heating effect, right? What's shown over here again is the comparison of transistors with the same number of total fins, but here by reducing the number of fins per finger and increasing the number of fingers, then the temperature increase that arises due to the self-heating effect is less, right? So that's what's being plotted here. The delta T, the self-heating, extra self-heating that goes on, is less when you have fewer fins per finger. Here you get a similar effect when you just take a given transistor and you just break it up, right? Into, like with the multiplier, right? You just connect more of them in series. It just allows more space and you get less self-heating, right? So that's not too surprising. But you can see the temperature increases there on the y-axis are significant, you just got a localized extra 20 degrees or so. So as far as the high resistance of those vias, the low-level metal layers like the M0s, the contact layer, right? I mean, usually, really the approach there is you just want to via up to higher layer metals that have less series resistance as close to the transistor as you can, right? To minimize that resistance. The problem there is that as you go up, right? I mean, you've got to respect all the design rule constraints while you do that. And that can be tough, right? And, even if you do respect all the design rule constraints, you're introducing tons of parasitic capacitances here as you go up, right? You just got more and more metal in close proximity to each other. So for example, the way it's shown here, you're kind of going direct via up as close as you can to the transistor, right on top of the source and drain region, if it's allowed, or as close as possible anyway. But what you'll end up with is CDS, right? A direct drain to source capacitance that, if you're an analog designer, that appears right in parallel with your RDS. So at high frequencies, it could kill your gain, right? So that's a tough trade-off to make. The alternative is to kind of route M0 out a little bit away from the source and drain region, and then contact up a little bit further away, the drain and source a little bit further away from each other. But as we said, M0 is highly resistive now, right? So, you've introduced extra series resistance with the drain and source, so that could hurt your GM and hurt your on current if it's digital. So that's tough, right? But a good thing about this style is if you route the contacts for the source and drain a little bit of a distance away from the transistor, maybe you can sneak in a gate contact closer. So you can get lower gate resistance, but then a higher drain and source resistance. The other style is like this, where you contact the drain and source right on top of the transistor, but then you have to route the gate out a little further. So you get more gate resistance, less drain and source resistance. So it's just kind of trade-offs. And that's why, you might say, why aren't all these parasitics, especially for the low layers of metal, why aren't they included in the device models to begin with? Because obviously you have to contact the device sooner. Well, but there's different styles, there's different layout styles you could take that might change that trade-off. So it's not usually, these parasitics are not usually included right in the base device model. And as a result, you can get a big surprise after you do layout, right? So this is another, style of layout that, you can play with, is just to try to trade these off by kind of, routing further and further away from the transistor as you go up gradually to try to trade off the capacitance, the parasitic capacitances against the series resistance, right? So there's a style that you can play with. Again, some of these tricks, may work in one technology, and then you go in a different technology and some different set of design rules kick in and you're just unable to adopt that style of contacting the transistor, and you have to totally try something different. So, all these complications, I should say, seem to increase the time that's required to do layout with FinFETs by quite a factor, like a factor of 3 or more, right? It just takes way longer to lay anything out and make a DRC clean because of all these considerations. It's no exaggeration to say that you can literally spend like weeks on just a diff pair, right? Just to optimize a few of the parasitics, not even the ultimate optimal design, but just to optimize a few of the parasitics and get a DRC clean could take weeks, especially for the first time you're doing it. So, although it's nice to talk about all these optimizations, in practice, what's usually done is you arrive at one layout style that kind of works, and you start using that everywhere. Or maybe you have two styles, a high-speed one and a low-power one, or something like that, and you just use those layout styles for the transistors everywhere. Otherwise, it would just take forever. So just a couple slides here showing an example of a FinFET design from our lab, because with all these headaches and all these challenges, you might say, well, why even bother doing this, right? Well, in this case, for this project, it was interesting because this project was interested in wireline communication that takes place within some of these huge data centers. So obviously, in a data center, right, it's very important to move bits very quickly, and but the circuits that are doing that job have to be integrated onto the same chips that have a lot of memory on them and a lot of computation on them. So, just purely for the density, for example, the density of the SRAM that you could get with FinFETs is so much better that those computational chips are always going to be in the most advanced technology available, and the communication circuits just have to be integrated with them. So even if it's not beneficial for those circuits themselves, it just doesn't make sense to do the research unless you're in that technology, right? You just got to make it work. So that was the case, and then here the circuits in this case involved the high-speed A to D converter, which is a lot of analog in it, which doesn't necessarily benefit from the FinFET technology. Some parts of it did, some parts of it didn't, and it had to all be integrated in 16 nanometer CMOS. And the layout was a huge exercise, took many months, and then here's just a quick snapshot of the result. But again, ultimately the outcome was worth it because it showed, the ideas that we were trying to get across, and they were applied in a FinFET technology, which is technology that would ultimately be required for that application anyway. So if you do it in a planar technology, I just don't think the research would have as much impact. People wouldn't be interested because, sure, so what if it works in a planar technology? You don't need this circuit in a planar technology. So just to conclude then, again, so summarizing, right, the whole, motivation was, we were looking for transistors that combine high on current, low leakage current, and a low supply voltage to give us a combination of high speed and low power logic. And FinFETs helped us do that because their geometry affords a lower transistor parameter N, which means a higher subthreshold slope, and less drain-induced barrier lowering. So both those are important. And they're sort of fundamental just from the FinFET geometry. So as a result, the FinFET technology gives us dense logic, so we can cram a lot of functionality onto a chip. We also, interestingly, get higher intrinsic gain for analog design, and little or no body effect, but there's significant disadvantages too. So notably, this layout's complex, and there's a lot of layout-dependent parasitics that are dominant. Reliability considerations, I would say, are also a big deal that impact all the layout styles you have to use. So, as a result, layout design in FinFET, is a bigger part of the design story. It takes a larger fraction of the time and has a greater impact on the ultimate performance. But again, in spite of all the challenges, there's some applications where doing the work in FinFET technology really helps the research have more impact. So that's why, we still need to do it. Thanks very much for your attention.